At the narrowest point between Maryland's two shores, more than 30 million vehicles a year funnel across a strip of steel and concrete that was never meant to carry the weight of the modern world. On summer weekends, it can take longer to cross the Chesapeake Bay than it does to drive across entire states. One crash can lock the bridge in place for hours. A strong wind can shut it down completely. And when that happens, Maryland fractures, with the eastern shore and the mainland suddenly cut off from one another. What's remarkable is not that the Chesapeake Bay Bridge struggles, it's that it still works at all. Built in the middle of the 20th century, the bridge was once a symbol of bold engineering and regional unity, but today it has become one of the most fragile links in America's transportation system. Engineers see the warning signs, policymakers see the risks, commuters feel it every time they inch across the span. The question is no longer whether the bridge needs help, but how much longer the old solution can survive a modern world. That is why Maryland is preparing for one of the largest bridge replacement projects in American history. Today, let's delve into the $17 billion Chesapeake Bay Bridge Replacement Project. Before we continue, a quick word about today's sponsor. If you work with PDFs often, UPDF 2.0 is worth checking out. It's a PDF tool we've been testing recently, and it comes with some useful features that make everyday work much easier. Inside UPDF, we can edit text directly, which is usually tricky in PDFs, and even change fonts while editing, which is genuinely useful. What stands out most is UPDF's inbuilt AI assistant. Powered by GPT-5 and DeepSeek, it lets us chat directly with a PDF to summarize or improve sections, like refining this CV. And for longer documents, it helps us quickly understand the content without having to go through every page. For sensitive files, UPDF also lets us protect PDFs with passwords and share documents securely. Beyond these, it includes a wide range of other practical features. UPDF works across Mac, Windows, iOS, and Android, supports one account on 4 devices, comes with lifetime free upgrades, and offers responsive customer support. There's a limited time offer available. Click the link in the description to check it out. The Chesapeake Bay Bridge, commonly referred to as the Bay Bridge, consists of 2 parallel spans crossing the Chesapeake Bay between Sandy Point near Annapolis and Kent Island on Maryland's eastern shore. The original span opened in 1952, followed by a second span in 1973, creating the primary transportation link for U.S. routes 50 and 301 across the bay. From the beginning, the bridge was built to connect Maryland's two shores in a way that transformed travel, commerce, and tourism. Over time, however, the very success of the bridge created its biggest weakness. It became the single most important crossing, and therefore the single biggest constraint on mobility between the two regions. Today, even with 2 spans, the Bay Bridge functions as a corridor bottleneck. It carries commuter traffic, commercial transport, and heavy seasonal tourism demand, all through a limited cross-section that narrows at the crossing. The result is a recurring pattern of congestion. The bridge has limited capacity to absorb disruptions. Lane drops, merging friction, slow-moving vehicles, and minor incidents quickly reduce flow. And once congestion begins, it tends to spread rapidly into the approach highways. Because there are no realistic alternate routes across the bay, delays become unavoidable and can extend for hours during peak periods. In effect, the Bay Bridge does not just carry traffic, it dictates travel reliability and controls access to the eastern shore. Beyond recurring congestion, the Bay Bridge faces increasing pressure from structural aging and safety constraints rooted in its original design standards. While the crossing continues to be supported through inspections, rehabilitation work, and traffic management, its physical configuration offers limited tolerance for modern operating conditions. In particular, the bridge provides minimal shoulder width and insufficient breakdown space compared to contemporary high-volume crossings, making it difficult to manage routine incidents safely and efficiently. These constraints have direct operational consequences. When crashes, disabled vehicles, or planned maintenance occur, there is little space to move obstructions out of active lanes or to provide emergency responders with a protected working area. As a result, relatively minor events can escalate quickly into major disruptions. Safety risks are further heightened by stop-and-go congestion, where sudden braking and lane changes occur in a confined corridor. The bridge also functions as a high-consequence link with limited redundancy. Weather-related restrictions or safety closures can interrupt service, and the absence of a nearby equivalent crossing means traffic cannot be redistributed effectively. Therefore, the bridge's challenges are not limited to traffic demand alone. They reflect structural aging and safety margins that are increasingly inadequate for the role the crossing is expected to perform. The Chesapeake Bay Bridge Replacement Project is being advanced through the Maryland Transportation Authority's Chesapeake Bay Crossing Study as a major corridor program to rebuild Maryland's primary bay crossing to modern standards of safety, reliability, and operational performance. Rather than extending the service life of the existing structure through incremental upgrades, the program is structured around full replacement, delivering new bridge infrastructure alongside coordinated improvements to the approach road network so the entire corridor functions as a unified system. The recommended replacement concept, identified as Alternative C, defines the project's physical build plan. It proposes 2 new bridge spans, each designed to carry 4 travel lanes with full shoulders, creating an 8-lane bay crossing with improved incident response capability and safer breakdown space. The program also includes widening and reconfiguration of approach roadways, supported by interchange and traffic flow modifications intended to reduce recurring congestion at the bridge approaches and maintain smoother corridor operations. Because the crossing must remain functional throughout delivery, construction is planned as a phased implementation. The new spans would be built and opened first, traffic would then be transitioned onto the new structures, and the existing spans would be removed after the replacement is operational. The program remains subject to federal and state environmental review requirements, including navigation clearance considerations, marine construction constraints, resilience measures, and mitigation commitments to reduce impacts on the Chesapeake Bay and surrounding communities. The Chesapeake Bay Bridge Replacement Project is being positioned as a long-term, multi-billion-dollar infrastructure program, with current figures still at the planning estimate stage rather than final contract pricing. Public reporting in late 2025 placed the replacement concept broadly in the range of $15 to $17 billion. Optional features can significantly shift total cost. For example, a shared-use bicycle and pedestrian facility has been discussed as a potential add-on that could increase the budget by $1 billion or more. These estimates reflect not only the cost of building 2 new bridge spans, but also the complexity of marine construction, phased staging to maintain live traffic, shoreline and roadway approach upgrades, and environmental mitigation requirements associated with building across the Chesapeake Bay. In terms of delivery, the project is not expected to move quickly. Reported timelines indicate that design development could begin around 2028, followed by a lengthy approvals and procurement period, with construction potentially starting as early as 2032. This extended schedule is largely driven by the Tier 2 NEPA environmental review process, a federally required stage that evaluates detailed project impacts, compares alternatives, and determines mitigation measures before final approvals are issued. Even with funding estimates and a broad timeline now taking shape, the project remains highly debated because replacing the Bay Bridge is not only an engineering decision, but also a political, environmental, and community impact decision. The first major challenge is environmental. Any large-scale construction across the Chesapeake Bay must navigate sensitive ecosystems, protected habitats, shoreline impacts, and water quality concerns. Marine construction activity, dredging requirements, and long-term changes to surrounding land use can trigger opposition from environmental groups and residents who fear permanent damage to one of the region's most important natural resources. This is one reason the NEPA process remains central. It requires detailed impact studies, alternatives analysis, and public hearings before final approvals are issued. Cost is another major source of criticism. A program estimated in the $15 to $17 billion range inevitably raises questions about affordability, long-term toll implications, and whether the investment will create additional growth pressure on the Eastern Shore. Critics argue that a larger crossing could encourage more development and traffic, ultimately recreating congestion at a higher volume rather than solving it permanently. Others question whether a highway-scale expansion aligns with broader climate goals, and whether transit or demand management solutions should play a bigger role. Finally, local tension is unavoidable. Communities near the bridge approaches face years of disruption from roadway widening, interchange changes, and construction staging. While the project is framed as a statewide necessity, the burdens, noise, land impacts, property concerns, and construction traffic will be concentrated in specific neighborhoods, making public acceptance a critical hurdle as the project moves toward final design and approvals. With funding and schedule planning underway, the project's long-term value rests on what Maryland gains once the replacement is delivered. The most immediate benefit is reliability. Wider lanes and full shoulders would reduce the cascading delays caused by breakdowns, crashes, and maintenance. This also improves emergency response, allowing police, fire, and medical services to move more effectively during disruptions. Safety upgrades are another major outcome. A modern bridge design improves lane geometry, increases recovery space for stopped vehicles, and lowers the risk of minor incidents turning into major traffic events. Economically, a more dependable crossing supports Eastern Shore tourism, commuter movement, and freight logistics across the region. Over the long term, the replacement is intended as a multi-decade asset, engineered to accommodate future traffic demand, withstand stronger storms, and reduce the need for constant traffic control measures that define the current bridge's operation. As planning continues and debates unfold, the project stands as a test of how modern societies confront aging infrastructure, whether they are willing to invest boldly in durable, long-term solutions, even when the costs are high and the trade-offs are complex. In answering that question, the Chesapeake Bay Bridge Replacement Project may ultimately redefine not just a crossing, but Maryland's vision of progress itself.